Okay, let's get started. So a few announcements before we actually do any physics. Homeworks. So your first online homework was available on Monday. It's due the following Monday. So Monday is the online tracking homework. This Monday coming up, we have a new lecture, which is available after lecture today. So there's two things due on Monday, and after lecture today, your first written homework assignment will also be available on Blackboard. That is due next week in recitation. So if you're a Wednesday recitation, it's due in your Wednesday recitation. If you're a Thursday recitation, it's due in your Thursday recitation. Okay, now before we get started, the clicker is actually working. So you should be able to see a start class notification in your clicker app. Check in, because very soon you're going to try and use said clicker. Okay, proceeding with the exciting physics of one dimension, which is basically moving along a straight line. On Monday, we decided to cover motion along a horizontal straight line. And we started defining certain quantities. Displacement is the change in position. The rate at which position changes is velocity. So velocity is defined as the rate of change of space. Basically, measure how fast an object's position is, probably thought of as speed. The reason we determine velocity is because we're now dealing with a quantity that has an magnitude of size, which is what we angular. So, along the straight line, we have only two options for directions. If we take one way is positive, the opposite of that is negative. Okay? What's plus and what's minus is completely up to you. Then we further on went and defined acceleration as the rate of change of velocity. Right? So it's in ordinary circumstances, objects will move at constant velocity. Their velocity is changing. The acceleration is a measure of that change. Right? So constant velocity implies moving with the same speed in the same direction. Right? Any one of these changes, magnitude of speed, how fast you're going, or the direction you're going in, there is acceleration. Okay? Any change in velocity is acceleration. And then we covered the kinematic equations, which are those guys there. The subscript x means we're talking about the x-axis. That's the horizontal axis. As you can see, there's the y-axis as well. The main pattern for these equations is constant acceleration. They apply to situations where the accelerating experience is constant. Okay? Right. Now get your clickers out, and Razvan is basically here for one purpose, and that's to drop balls. There's really not much one can do in one dimension, right? We're restricted to moving along a straight line. We can either drop the balls or throw them up. Oops. Dropping is easier. I know this said that there is a racquetball, but a racquetball is just another kind of ball, and he has two hands, so he's going to drop two balls. All the way there so that they can actually fall. But before he actually drops them, you guys are going to tell me, yeah, the pole's open. You guys are going to tell me which one lands first. So there is no C. It's either A or B or D. Okay. Isn't that fun? Does anyone manage to actually click in? I'm not seeing anyone actually clicked in. Sorry?
It says that we're in the class, but then that doesn't come up.
So you're not seeing that? Oh, isn't this fun? I knew there was a reason this was free. Okay, I'm going to stop that poll. Has everyone actually managed to... Okay, I have a solution. Maybe. Okay, are you guys actually still checked into the course? Great. I should be able to pull up. I'm going to turn that off for a quick second. Yeah, this is fun. Meanwhile, you guys should be thinking about what actually lands on the ground first. Yep.
My clicker is not even recognizing me in class.
It's because I just turned it off. Okay, can you guys see that now? I have one response. So someone actually managed to click in. Great. So it's finally working. Okay. Let's recap. The question is, he's holding two balls in his hand. He's going to drop them both at the same time. Which one gets to the ground first? Well, I mean, the nice thing is you guys can click in your response and I can kind of see what you say before he actually starts dropping stuff. Okay, so click in if you haven't. I'm going to give you guys another minute or so to click something. By the way, participation is measured by your clicker, not by whether you get it right or wrong. Okay, so you have to just click in. If you're here and for some reason your app is telling you that you're not checked in, see me after class. It should clearly indicate to you whether you guys are checked into class or not. Okay, let's go with that's done. And now let's see if I can pull up the answers. Great, so I didn't mean to squeak. Okay, so yes, most of you got it right. They basically land at approximately the same time. Some people just wanted to point out that I didn't have a racquetball, right? Okay. Right, so they both land at approximately the same time, and then this, oh yes, he's going to actually drop them. Right, so I know it's not very exciting, right? The only other thing he can literally do is throw them up, because we're restricted right now to traveling along straight lines, right? So he can walk back and forth with the balls, or drop them, or go up and down, and that's it. Right? Now he's done dropping balls, and they land at approximately the same time. And now let's just say that I have two actual masses, right? A 10-gram mass and a 1 kg mass. And I drop those, which is pretty similar to dropping balls. Which should land first? Right. So go again. Okay, click something. Very good. Both land at approximately the same time. Now, this question is the same question as the balls question, simply because what you're talking about is two objects in free fall. Right? Anything in free fall experiences the same acceleration due to gravity near the surface of the earth. If I took a piece of paper, for example, and a bowling ball to the top of Fox Hall, and I decided to drop them, like in reality, which one would hit the ground first? The bowling ball. Right? Because of air, right? So the piece of paper experiences significantly more air drag, right? So in the absence of air drag, right, a bunch of feathers and a bowling ball should all experience the same acceleration in gravity. Right? Picturing a situation without air is actually not that hard. There's a video. So that's a video of a bunch of feathers and a bowling ball in a vacuum chamber, which basically means there's no air. Right? And they fall with the exact same acceleration. Everyone with me? So in the absence of air resistance, and air resistance is something we'll discuss eventually, but all you really need to know is that we've neglected for the most part. And it's generally an effect that's felt at high speeds. The force of air resistance increases the faster stuff is moving. So like when you're riding a bicycle and you're just riding along nicely and you stick your arm out, you experience a little bit of air. Right? But if you're driving a car with someone like me doing the driving, and you stick your hand out, you experience a significantly more amount of air. Right? I do drive faster than a bicycle. So the amount of air drag is actually related to the speed at which stuff is moving. The faster it's moving, the more air drag it experiences. As far as gravity is concerned, which has nothing to do with air, anything near the surface of the earth, if you neglect other forces, right, if it's just a free fall, will fall with the same acceleration regardless of its mass. Right? The why of that we'll study with gravity. But for now, since we're concentrating on motion along a straight line, and our next topic obviously is motion along a vertical straight line, right? The one thing you want to bear in mind is in the vertical axis, right? If you have nothing else, just gravity acting, there is acceleration. Right? And that acceleration is 9.8 meters per second squared, pointing in a specific direction. Someone's going to be the direction of acceleration is that. Does gravity point up or down? Down. Right? So acceleration due to gravity, that 9.8 meters per second squared, points down. The plus or minus that you use is up to you. Right? Because plus and minus are defined by you. Right? You have a vertical straight line. If you say going up is positive, then the value of g is minus 9.8 because it points downwards. But if I say going down is positive, then the value of g is plus 9.8 because it's going downwards. Does that make sense? Right? What is true is that near the surface of the Earth, g is 9.8 meters per second squared and it points down towards the center of the Earth. Right? You're choosing a plus and minus shouldn't change the fact that g points downwards. That makes sense? Okay. Right. So the other example, of course, is throwing a ball up. So when we analyze throwing a ball up, right, the first step is pick a coordinate axis, right, which basically means pick which direction it's going. Okay. So in this example, I'm picking up the ball. Okay, which means that the acceleration is minus. Okay. So if I toss a ball up, it's going to do that, right? It's too bad I sent him away. I'm going to try tossing my phone. If I drop it, it's your fault. So I toss it up. How high it goes depends on what? Its initial speed upwards, right? I can't change anything else. I can't move to a different planet and get a different acceleration to gravity, right? The only thing that determines how high this thing goes is how fast it's moving when I throw it up. That makes sense? Right? The difference between a nice safe throw and an oopsie throw is the speed it moves when it's being landed. Correct? And then it does this. It basically goes up, right? And as it's going up, what's happening to velocity? Increasing. Decreasing. Right? So if v is pointing upwards and it's decreasing, the term acceleration is pointing inwards. Off or down. Right? Goes all the way up at the very top of its motion. What is its speed? 0. Right? It's changing direction. Right? And then it starts to fall back down. When it falls back down, is what's happening to the velocity up, down, or stays the same. It's going up, right? The velocity is increasing. Which is again what you'd expect if v and a pointed in the same direction. Right? So throughout this motion, acceleration points straight down. It was changing its velocity. Right? Displacement is changing, velocity is changing, acceleration is constant. Okay? Right. So let's say I tossed it up with the speed v1. That arrow there is showing you the direction of A, which is downwards. You toss it up, slows down, comes to rest, falls back down with increasing speed. Right? How fast is it moving if I catch it at the same position where I am? If I toss it up at the speed of v, right, and then it go up and come back down, how fast is it moving when I catch it again? The same, right? Now if I was to ask about velocity instead, if I tossed it up with the velocity on its, when I catch it on its way down, what was the velocity? Minus. Does that make sense? Right? Because velocity includes direction. I've taken up a positive, so my initial velocity is a plus v. Right? On its way down, it's moving in the negative direction. So the final velocity is a minus v. Does that make sense? Right. And the actual motion can be analyzed using these. Right? These are your kinematic equations that you saw on there. And all I've done here is substituted A is equal to minus B. Right? So the presumption in using this form of equation is not equal to that. Right? So the presumption in using this form of equation is that output is positive. Right? Because I substituted A is minus B. Correct? If on the other hand I decide to solve my problem using downwards positive, right? All those minuses in front of G become positives. Okay? And of course, if I choose downwards positive and I toss a ball upwards, the initial velocity is minus v. Right? So every time you pick a coordinate axis, right, stick with it. and then look at the quantities and see whether they're pointing along it or against it. And that determines whether they're plus or minus. Right. So problem solving. We're going to do one on slides, and then I'll do one on a doc cam. So we're dropping a ball from rest 22 meters above the ground. And we're asking you for the final velocity of the ball just before it hits the ground. So if I'm dropping a ball, what does that do? The very act of dropping a ball gives me an initial condition. The initial velocity. Right? There is a difference between dropping a ball and throwing it. Right? I can throw a ball without initial velocity, but I can just drop one. If I'm dropping it, the initial velocity is zero. Correct? Okay, so I'm also told that this ball is 22 meters above the ground. So my first step is draw a diagram. That is the dropped ball. Label all the quantities that you know. I know I dropped it from a height of 22 meters. And this, by the way, labeling it this way sets my coordinate axis, right? I have 0 down there and plus 22 up there. So that means this question is being solved taking upwards positive. Correct? Okay. My V0 is 0. That's my initial velocity. And then the acceleration, of course, is minus 9.8 meters per second squared because we take it upwards. Does this make sense? Yeah. So I can do the same question, right, by saying my starting height is 0 and my ending height is 22. Right? That is 0 is up here, 22 is down there, that means downwards is positive. Correct? But if I take it downwards positive, acceleration due to gravity, little g, which points downwards, is a positive number. Right? Because whatever you take as plus or minus, you flip the direction of the little g. Right? Acceleration due to gravity near the surface of the earth will point down towards the surface of the earth. Okay, so when you take it downwards positive, it's a positive number. If you take it upwards positive, it's a negative number because upwards positive is pointing downwards. Does this make sense? Right? Do not get bogged down in pluses and minuses. Those are arbitrary. Those are your choice. Right? But your choice shouldn't mess up the actual result. Okay? So since G points downwards, anything that takes downwards positive will have a positive G. If you take upwards positive, you'll have a negative G. Okay? Right. So this question took upwards positive, and so my acceleration is minus 9.8. Then you make a table. Okay? Get into the habit of making these tables. Right? Put down what you know and what you do not know. And then you have the kinematic equations. Use in a way that makes sense. Right? So if you look at your list of stuff you know, time isn't on there. Right? Moreover, the question hasn't even asked me for that. Right? It's not asking me how long it takes to get to that. It's asking me how fast it's moving. Right? So I can solve the time, but I don't need to. Everyone okay? Okay. So the equation that makes sense in this scenario is the third one. It doesn't have any time information. It doesn't require any time information. I'm looking for the final velocity. I have V0, I have A, I have the displacement, x minus x0. Right? So I'm going to use that one. Plug and chug into it. Those are your numbers being substituted. Whenever you work with kinematic equations, make sure all your quantities are in SI units. So spend a couple of minutes converting anything that's not in SI units to SI units. Right? And the SI units of speed are meters per second, acceleration of meters per second squared, displacement is meters, and time is seconds. Okay, so plug it in, solve for V. You get v squared is that much, so v is the square root of that, which gives you a final answer of v is either plus or minus approximately 21 meters per second. Is the correct answer in this case plus or minus 21? Formula. Minus, because there's a couple of positive and this one is moving down. Does that make sense? The question, of course, starts with speed. Speed is just the magnitude of that. In one dimension, it's the meters per second. It's moving 21 meters per second downwards. Okay, now you guys have pen and paper in front of you. The kinematic equations are up there. I'm now giving you time, and I'm asking you how fast this object is moving. If it starts with rest, it falls for 10 seconds. Now remember, free fall for 10 seconds is not like a small amount of time. I mean, imagine something jumping off a foxhole, and imagine how long it takes them to fall down. I mean, don't literally imagine people jumping off a foxhole, just dropping balls off a foxhole. This question is asking you to find final velocity. It's giving you time, and you should know acceleration. Right? And you know v-initial velocity. So the equation that makes sense is the first one, the second one, or the third one? The second one, right? The second one will make your life very straightforward. Okay, click something. Remember, it's the click itself that determines your participation grade, not whether the click is right or wrong. So you have to click. Okay, I'm hoping everyone's clicked in. And no. The bright side is everyone's clicking the right answer for the most part. V is correct. It's 98 meters per second, right? It's that. Right? V is V0 plus AT, the second equation. We're looking for V. V0 is 0, we start at rest. A is 9.8, T is 10. So 9.8 times 10 is 19. Right, now let's say I asked you instead of its speed, I'm looking for how far it fell. So think about this question. It's actually asking you to tell me how far does something have to fall for it to be in free fall for 10 seconds? Which equation makes sense here? It should be like a checklist in your head. What do I know? What do I not know? What am I looking for? Right? I know in this case I'm looking for displacement. Right? How far I fell, this is. Okay, so I'm looking for x. I know v0. I know the initial velocity of the system is 0. Right? I know acceleration. Taking downwards positive and acceleration is minus 9.8 meters per second. Okay, let's see where you guys are at. You should be clicking in happily. Well, not necessarily happily, but clicking. Okay, I'm seeing a positive trend here. When I say I'm seeing a positive trend here, it means I'm kind of happy that the answer is correct. Okay, click in if you haven't. And by the way, when I get to the click in if you haven't stage, just click something so you get the attendance credit. Okay, and the correct answer is D, and you get that from using the first equation, and the only term in that left is x is 1 half t squared. T squared is 100, that's 10 squared, times 9.8 is 980, times 0.5 is 490, right? And physically, that's a fair amount of distance. That's half a kilometer, right? It's almost 500 meters, okay? Like, for a reference point, I am, on a good day, around 1.5 meters, okay, on a good day. So you can imagine like 400 of me stacked up, and that's probably less tall than how tall that was to be in free fall for. Does this make sense? So free fall is, it's a big assumption. In order for something to be in free fall for 10 seconds, it has to be falling from a pretty enormous height, right? And generally, stuff moves faster as it falls. So remember at the beginning we said neglect air drag? It's not always possible to neglect air drag when stuff is falling from very, very far, right? Because it's moving pretty fast, correct? And generally, when stuff is thrown out from really high things, it achieves something called terminal velocity, right? And terminal velocity is basically your equilibrium point between when the air drag balances out gravity. If there's enough air drag to balance out the acceleration due to gravity, it's falling at a constant velocity, and that's what we call terminal velocity. Okay? In the scenarios where we say neglect air resistance, there's no concept of terminal velocity because it comes because of air resistance. Okay. This is not a math question. I'm looking for V and A, right? Magnitude of the velocity and the acceleration at the highest point in the motion. So this is a ball tossed straight up, right? At the very top of the motion. What is the value of velocity and what is the value of acceleration? There's no plus and minus in this because they're not math, right? So plus and minus is directions. Right? So magnitude is just enough. So we know that at the very top of the motion, the velocity is 0, right? It's momentarily at rest before it falls back down. So the correct option is either A, B, A or C. E is generally never right. Okay? I will always give you enough information. Unless it's but, so your options now are either A or C. Option A comes up a lot. And remember what V equals 0 and A equals 0 actually means, right? It's something that's simultaneously got 0 velocity and 0 acceleration. What does it do? Nothing. It is at rest, right? So that V equals 0 and A simultaneously equal to 0 is true of an object at rest. If I toss a ball off at the very top of its motion, it doesn't just go there and stay there. Correct? Its velocity is continuously changing, which means that even at the very top, there is deceleration. Everyone with me? Okay. So the option must be C. The value of A is the same throughout the motion. It doesn't change, right? Free fall is motion at constant acceleration. And when we say something is constant, we're saying that it doesn't change, right? Okay, so let's see where I'm at. Great. That is correct. The answer is C. Okay. You can picture the fox burrowing into something, but that's if you want to. But this is the same. A fox going up and down is the same in physics as a ball going up and down, or a professor going up and down. Right? It's an object going up and down. So during the entire motion, it's free fall. And you're looking for a velocity and acceleration, like velocity and acceleration curves that describe that motion. Right? So think about what's happening to velocity. As the ball goes up, what's happening to velocity? Increasing or decreasing? Decreasing. Right? The ball, the fox, right, slows down on its way up. Correct? Okay. If you look at the three curves for V there, right? A, B, and C. In A, if you look at just the magnitude of V, right, what's happening to it? Is it increasing or decreasing? Decreasing, right? Becoming smaller and smaller magnitude. Correct? In the beginning. In B, what's happening to the magnitude of V? Decreasing, right? Becoming smaller and smaller magnitude. Everyone with me? So both A and B satisfy the fact that as this box is going up, it's going down. Right? But if you look at C, it's telling you that as that object went up, it sped up. Correct? So the answer is not C. Okay? It's either A or B. Now, look at the difference between A and B is the direction. Right? So, if you look over there, if your acceleration is positive, right, that's the correct slope for A. But the question tells you that the plus y direction is pointing downwards. So can A be a positive number? No, right? Because acceleration due to gravity is pointed downwards. Right? So if my y-axis points upwards, acceleration due to gravity points downwards. And that is B. Right? It's a straight line, it's constant acceleration, right? But it's minus 9.8 meters per second. And it is, of course, the slope of the first line. Okay, so very good. Click something if you haven't. And right. So this is the upwards positive jump, right? And you can see that V is decreasing. Everyone agree? At that point where it crosses the axis, V is instantaneously zero, right? Which in terms of the fox is the top of the fox's leap. That's where this fox's speed is instantaneously zero, right? It's changing direction. Correct? Then it falls back down, and as it falls back down, its speed or its velocity becomes more and more negative. So it's moving faster in the negative direction. Right? That's what that line is. And it has to be a straight line. This is motion at constant acceleration. So V versus T will be a straight line. Okay? And A is just the slope of that line, which is minus 9.8 meters per second squared. Okay. Before we actually go to that, if we go back to so this is the VT curve, right? That we were just discussing. Okay. If I want to look at displacement versus time for the fox, What should that look like for this curve? What is the displacement versus time graph for that curve? What's happening to the box of displacement? A parabola, which should look parabolic, right? So it looks something like this, right? And the slope at every single point is the velocity of this thing, right? At the very top, the slope is 0, which is that point, right? Beyond that, it turns, and as it comes down here, it starts picking up speed. So the slope is becoming more and more negative. Everyone following? Right? And this, of course, corresponds to an A versus T graph that looks like this. Okay? So remember this. If you have a straight line in V versus T, right, the velocity versus time is a straight line, implies a motion in constant acceleration. Right? You can find the slope of that line, and that slope is the acceleration. And if you have motion in constant acceleration, displacement versus time will be parallel. Right? It's a t square dependence on displacement. So it looks parabolic if it's constant acceleration. Okay? Right. Now let's do another actual problem. So this question asks for a little bit of math, and that's the split screen. So all we're telling you here is that the ball's initial speed is v. Okay, there are no numbers. I have only what the initial speed is. All I'm asking you to do is find how high will the ball go. Right? And this answer should be expressed in terms of v and v. Everyone with me so far? And I don't actually have to give you a number, I can give you a variable and ask you to express the answer in terms of that. Okay? So I know my initial speed is v. So I'm tossing a ball upwards. V0 is v. It goes up. V over here, I'm going to call this v final, is 0. Okay? Now, what I'm doing here is breaking up this motion, right? This motion is perfectly symmetric. The time it takes for it to go up is equal to the time it takes for it to come back. Right? The speed with which it's moving initially is the speed with which it's moving when it comes back. Right? So I'm breaking up this motion, going up and going down into two separate pieces. Right? And we'll just treat it as going on. If I just look at that part of moving, right, then I know that I start with the initial velocity of v. I have a final velocity at the top of 0. Correct? And I have an acceleration of minus 1. Okay? And what I'm looking to do is find how far up does it go. I'm not given any time information. Right? So I do not know time. Right. I know v0 is v. I know v final is 0. I know acceleration is minus g. I'm taking upwards positive. Okay? The equation that makes sense to use in any scenario where I don't have t is the third kinematic equation, which was v squared is v0 squared plus 2a delta x. This is 0. This is v squared, 2 times minus g times x. I'm solving for x. X is how high it went. Right? So x comes out to be v squared over 2g. That is how high this thing goes. Right? And the answer is in terms of the variable I gave you, which is v, and the constant, which is v. Okay? Now, if I were to ask you, what is the total displacement of this ball during this motion? What would the answer be? 0, right? It went up, came back to the same position. The total distance during the entire motion. Right? Total distance traveled would be how much? That much. 2 times that, right? Okay. Now, the other question I could ask the boy is, how long did this entire process take? So if I'm looking to find time, right? Let's use the second kinematic equation, which was V is V0 plus AT. I know my final velocity at the top is 0. My initial velocity is V. A is minus G, right? Solve for T. You get T is V over G. Here's my question. Is that the total time of flight? That's the time it took based on what I decided, but is that the actual time of flight? It's half the time. Right? The initial conditions I've used to solve this are V is 0 at the top, so we're talking about half the motion. Right? The total time of flight is the full motion, time it takes to go up and come down. Right? We use the fact that it takes the same amount of time to go up as it takes to come down. So if I know it takes V over G to go up, it takes 2V over G for the whole motion. Everyone with me so far? So that's kind of how you solve problems in one-dimensional kinematics. You draw a diagram, label the axes, figure out what you know, figure out what you're looking for, and then set up the equations and solve for the unknowns. Okay. One last thing before you guys actually get to go. You will do this in presentations. It's a question on your presentation worksheets. But the idea is crumple zones. Why do you have crumple zones designed into cars? Why are cars designed to crumple when they hit something? Sorry? If they crumple, you won't? Yes, that's kind of true. So the whole idea with a car crumbling is to extend the time of the collision. Right? What happens in any accident is you have a starting initial velocity and you have a final velocity of 0. Right? Me running into a tree, my final velocity is 0. Right? What determines whether or not I get hurt is how fast I came to a stop. Right? How fast that velocity changed to 0. So by extending the amount of time for collision, you reduce the acceleration experienced by people. Right? You reduce the acceleration, you reduce the chance of injury. Okay, I will see you guys right away. Do not forget